Okay, so I'd like to welcome Igor today. Igor is it's a colleague of mine that I met when I started my PhD, and then we worked together in several projects, and including our startup Rexis Labs. And he's an expert in information retrieval, in machine learning, a recommender system. He's really good in many things. So I'm really honored that he has given us his time today, and that he's with us. So thanks, Igor. And yeah, please begin.
Great. Glad to be here. Yeah, so Claudia asked me to give a tutorial on something that might be useful for people, not anything too technical and not anything too academic, because what often happens is you get carried away learning about fancy algorithms or latest and greatest GPU art generating thing, and you ignore some of the more kind of basic things that become huge stumbling blocks after a while. So my whole idea is just to introduce a couple of really good kind of techniques and kind of heuristics almost for dealing with the kind of size of a data set that is slightly uncomfortable to deal with on a single machine, but not too insurmountable. So there's very small data sets that are trivial to process and take seconds to do anything with. And those are usually the kind of demo data sets that you might encounter, or the benchmark ones. And those aren't really that interesting because they're not very realistic. You don't see many tiny data sets in the real world. And on the other end of the scale, there's these huge data sets that necessitate some sort of massive cluster for processing them, where you have an already well-established pipeline for processing a lot of stuff that's coming in, constantly training models, constantly running something, experiments, and that kind of stuff you really need a team of people for. And what I'm aiming for is something like Kaggle size, maybe, is a good way to describe it. So it's just you on your own on your laptop or in Colab, and you've got a chunky data set where it's a little bit unwieldy to work with. So you got to figure out some way to make it kind of easier so you can adapt it and try some stuff and see if it works. Because otherwise, if you just dive straight in and don't do anything and just do it the naive way, you're going to be sitting here for days looking at a progress bar. So one of the things I would kind of immediately point out is that no matter what kind of data you're dealing with, at some point you're going to start slowing down. There's going to come a stage where the data will grow to the point where it'll outgrow the memory, the hard disk space, or the some other GPU resources or something like that, and you're gonna find yourself where you're gonna have to optimize something, either start working on smaller subsets or doing something in an alternate way so that it's manageable. And I have to mention, the easiest way to do that is just to throw money at it. And in Colab, the easiest thing in the world is just to pay for the paid Colab tier, where you get more RAM and better CPUs and better GPUs. And unfortunately, you don't get that much more RAM, though. I think it's you still end up with 12 to 20 gigabytes. But that's kind of one very obvious way of solving this problem of dealing with these medium-sized data sets where you're just approaching the threshold where you can't process it. You just throw some money at it and get a bigger instance. I will mention though that personally, it's more of an opinion. I wouldn't, well, you got to make up your own mind for that, but I don't think the Colab paid plan is worth it. I think what's worth it is buying Google Compute Engine instances specifically for a job and using that one. So the way it generally runs is you can have a custom Google Compute Engine VM that you pay for separately on Google Cloud. And you can set the resources that you require specifically for whatever it is you're doing. Maybe you want like a better GPU, maybe you want a load of memory, maybe you want a load of disk space. So those are the things you can optimize and pay for a VM per hour and finish paying for it once it's done processing. Whereas the monthly payments, I don't think they're worth it in the end, unless you're very heavily using Colab, like daily. That's just an aside that I would mention. Yeah, so yeah, so you've got a bunch of resources. By default, they're kind of random. Sometimes you get a really good instance, sometimes you get a really poor one. There are floating around a couple of tricks for Colab where supposedly if you make it run out of memory, if you fill the memory just with junk and make it crash, sometimes when it restarts, it gives you an instance with more memory as a kind of as a way to entice you to pay for it. They kind of advertise it this way, but that's very not reliable. I tried it earlier and it didn't work for me for the last like couple of days when I was looking through this stuff. So I wouldn't rely on those things, even though there are a couple of tutorials out there where it's like, well, the default resources won't be enough to run this, but if you crash the thing and get a better instance, maybe you'll get it, but I wouldn't rely on that. So one of the first things I would do is maybe be aware of what your hardware limitations are. So on Colab, you can have a quick look at what kind of CPU you have. The most important thing I would look for is the number of CPUs and maybe number of threads as well. So the reason for that is sometimes you get a single core, and in Colab, that means that any of these techniques that split data with multiprocessing and try to use multiple cores to process multiple chunks at the same time, that's not going to give you much of an advantage if you've only got one core. Like over here, you've got two threads per core, so it should still work out if you give it like 4 separate workers that are going to be working in parallel on different chunks of the data. So it might be worth doing it that way. But if you ever see like a single CPU core, you'll know not to bother with multi-core stuff because you just don't have the hardware for it. There's a bunch of stuff you can learn from some of this other output where it shows off what instruction sets it has and all of that, but as a rule, the Colab runtime is already optimized for all of this, so nothing you do here will matter much. This is more maybe useful for your own workstation or your own laptop. Sometimes it's worth Checking out your hardware, seeing what features it has and whether or not your software is making use of them. So the perfect example is like in Python, on Intel CPUs, there are certain optimizations that you can put in for NumPy that will make things like 20 to 30 times faster, almost as much as going from CPU to GPU for some types of workloads. And that's one of the easiest wins you can have, is just keeping your software up to date and correct. So for example, Conda for Python will install these numerical libraries by default, and they're already pre-compiled. Doing that yourself is kind of a little bit involved. I wouldn't recommend it. I would more recommend looking for a good package manager that will manage this stuff for you. But anyway, since we're working in Colab, all of that stuff is already done. So Colab basically hosts your notebook, and it's got a virtual machine in the background somewhere, and it's running a Python interpreter, and it's got a bunch of resources allocated to it. So you don't need to worry about any of that. As a kind of overview, you usually get a good chunk of hard disk space. So that's usually not a big blocker, although the performance can vary quite a lot. CPU affects things that are compute band. Types of hard drives will affect your I/O, so how fast you can physically read stuff from the disk can sometimes slow you down and be a limiting factor. But as far as I've noticed, there's not that that rarely happens in Colab. If you're doing something super disk heavy, I would go back and recommend switching to a Google Compute Engine VM that has like SSDs and has like a guaranteed provisioned performance for disks, whereas over here it's more you write out a bunch of temporary files and you use them and you get rid of them afterwards. Memory, I think, is maybe the thing that is going to trip you up the most. So that's the thing I would focus most on. So by default, Colab gives you, well, it says 12, but really, even without it running anything, it's more like 10. Because you can see already there's like 2 gigs being used just from the thing running on its own without loading any data. And I'll explain later on, and go in a bit more detail about managing all this stuff. But sometimes this interface will lie to you and make you think that you have more resources than you do, and then you get a nasty surprise when you try to run something and it crashes and you got to go back to square one and restart everything again. Oh yeah, so sometimes if you get a GPU instance, you end up with more resources, but I think they got rid of that now. So right, we're not going to be using any GPU stuff, although there are a couple of libraries. There's an NVIDIA library where you have GPU accelerated data frames, and it's a drop-in replacement for pandas. That's also a thing worth looking into, but I won't go into it today. That's something maybe you can check out yourselves once you kind of poke around all the different versions of Python and all the different versions of pandas and see which one is most optimal for whatever it is you want to do. So yeah, just so in case you haven't seen it before, all the exclamation mark cells are as if you're running a terminal. So there is a terminal in Colab, but you need the Pro account for it. But if you don't have a Pro account, you can just run single terminal commands one by one with the exclamation point. And you're going to need it because that's how you install different packages. So for this one, as a kind of motivating example, I took a data set that I crawled a couple of months ago about air travel. It was a load of tweets, and just to demonstrate how to handle these large data frames, we're going to run some very rudimentary sentiment analysis on it. Not really for any point. I'm not going to go into like actually analyzing what's in the data or doing anything useful with it. I thought I'd concentrate purely on the kind of data janitor steps that often get overlooked. Usually with things like this, you get like a nicely cleaned up data set and it appears out of nowhere. And that's usually 90% of the effort goes into cleaning this stuff, going from the original data to something of a flat structure that you can visualize, and then kind of iteratively looking at things and taking stuff out, putting it back in, mangling it somehow, and so forth.
Igor,
yeah.
Sorry to interrupt, but there is a question. So could you explain again what the exclamation mark does?
Oh yeah, sure. Yeah. So the normally when you create a new code cell, it's Python. So any Python command will work. All of that. But if you want to run something outside of Python, if you want to run like a bash command, you can use the exclamation mark, or you can also use the cell magic, I think. So cell magic is a % and something. Oh, it's double %, is it? I can never remember. Yeah, it's double %. And then something. So it's two ways of doing the exact same thing. Instead of executing this cell as Python code, you're executing it as bash prompt command. So something that you would execute on your own machine that's just in the command line. Like pip install will modify the Python environment. And one of the gotchas in this is after doing a step like this, sometimes you need to restart the runtime for the changes to take effect. So what happens now is I have installed a couple of new packages, and they installed a bunch of dependencies. So now it's better to restart the runtime, which will, it won't give me a new kind of virtual machine instance, but it will restart the Python interpreter that's running in the background. So if I wanted a brand new machine, I could disconnect and delete the runtime entirely. But if I want to just restart it, that's usually faster, and it keeps keeps some of the disk and other state intact while getting rid of all the Python stuff. Whereas disconnecting and deleting the runtime deletes everything completely, even the temporary files like you created and all of that. So if you really screw up, you can delete and disconnect the runtime and start from scratch again. If you just made some changes and something's not working, or some variables got overwritten or something, usually restarting the runtime and rerunning the cells is enough. So yeah, this one's actually a good example of something that persists across restarts of the runtime. So I got some data already loaded in my Google Drive, and this small snippet of code just mounts my Google Drive as a folder in here. So I have my Google Drive with my data sets. I've got a bunch of them. Yeah, this is the one we'll be working with. It's a data set of air travel, and I've already created a bunch of files in here. So when I restart the runtime, the mounted folder doesn't go away, even though this cell is no longer active and this never got ran. This persists across restarts. So anyway, just to kind of catch everyone up on where does data come from and what is it and how it came to be. I'm not going to be running these things, but I'll leave them in anyway, just for an explanation. So it's more installing some packages. Twark is a command line tool to get Twitter data. It makes it a lot easier to convert things.
Igor.
Yeah.
So yesterday I mentioned a bit about Twark because I also showed some archived Twitter data that we collected, and it was about Malawi as well with the floods.
Yeah.
And I think there was a question about if it's similar to an R library, right? It was about. Could you please?
Yeah. Any
Yeah, my question, sorry, it was if it was similar to academic Twitter in R. Yeah,
it's actually, it fills the same or tries to perform the exact same function, except, okay, I'm a little biased because I'm a Twark developer, and I contribute a lot to it, and I think Twark does it in a better way. Especially, we'll get to it in a while, but you'll see why Twark does it better in a while, because of how we process the data that's Twitter specific, whereas the R library does it in a more generic way, and it leaves a bunch of records in a different state. Anyway, I'll explain now. Maybe once I show you some data, maybe I can explain. But obviously, my point of view is extremely biased because I wrote Twark CSV, and that's like my thing of converting tweets into data frames. So obviously, I'm going to recommend this one and not the R one. But my bias against R is purely not rational at all. I just don't like the syntax of R. That's my gripe with it. I actually think the R visualization and the statistical models are far superior to what's available in Python. So if you know what you're doing with R, you can be much more productive than in Python. So what I actually would recommend, if you're familiar with R, is convert the data with Twark. So it generates a better format of a data frame and then import it back into R and work on that one, rather than using R to convert the tweets from JSON to CSV, like a flat thing, which is what I'm going to explain next. So just for some kind of background in Twark, you issue some commands and it basically just writes exactly what it gets from the Twitter API. So let me see. This was the original command I ran. So it's a search that spans from 2015 to 2022, and it includes tweets that have air travel or air transport or flight and holiday or vacation in it. So any tweets that mention that.
So yeah, just one thing from yesterday. If you remember, I showed you a query like these two, but it wasn't. It didn't have the terms. So this is a really good example of how you can actually go in with terms already that filter. So those are or and terms that should be in the tweet for it to be relevant. So yeah, so it's something else that you can add to the query that I showed you yesterday.
Yeah, maybe it's worth. I'll just quickly unpack this thing because it applies to other things too. So I'll stick it in a new code cell. So this is like an original query for the Twitter API, but there's a small kind of bit of syntax mess with it because it's in a command line, and the command line expects double quotes to surround parameters. You need to escape the inside double quotes that define phrases in the search query. So the search query is actually more like this, which is slightly easier to read. Yeah, so we have, if the tweet has the phrase air travel or air transport, or has the word aviation or airplane, fly or flight, and that's like one term because there's brackets. So if it matches any of these cases, and then the space is an implicit and. So it's like if any of these things are true and any of these things are true together. So it has to have both one of these and one of these in any kind of combination. And that's what the original query is. I guess it's getting this query right kind of depends on what your goal is. But for us, it doesn't really matter so much. Just to be aware that all of these tweets will have this kind of thing in it. So all of them will be extremely similar to one another because they're all talking about the same thing, just to kind of look at it. So what you end up with is a bunch of responses inside a text file. And each one of these, I had it open here. So each one of these is maybe this way is better. It's a lot of data in one object. So you have 481 tweets inside a list with a whole bunch of different metadata that goes along with it. So there's 623 users that have been mentioned or are authors of these tweets. There's 37 pieces of media somewhere in there. There's other tweets that are referenced within here. There's geolocations and places. Well, always a couple of errors and some other metadata that's in there. So it's a lot to pick through, and each tweet then contains even more metadata about itself, and it references other bits of metadata. So there's a lot of stuff here. Not all of it is useful. Some things you can get away with not even loading in the first place. So you might be interested in how many times something has been retweeted, liked, or replied to, but you might not be interested where the tweet was sent from. So you can exclude certain fields or entire sections of this. And that's kind of what we're aiming for. We want to be able to just get like the minimum useful representation of this later on. So the original data comes in the form of separate responses that have nested tweets and nested data inside it. And that's very difficult to work with. It's better to work with this kind of data if you are writing this directly to a database and you already have separate tables for tweets, separate tables for users, separate tables for all these other objects. And this kind of structure then makes sense because you have one response and then you can make a transaction and update your database with all of these all in one go. And that kind of makes sense from looking at it as a record-based system. But for any kind of data analysis, you're looking at it in a separate or in a kind of orthogonal way. You're looking at it column by column as opposed to row by row. So rather than looking at it one record at a time with a set of tweets, you ideally want to be looking at things one column at a time, which is across all tweets. Maybe it'll make more sense once you see the data frame kind of visualized. So there's a couple of other Twark commands that are helpful. So turning a data set of API responses into tweets per line where is sometimes worth it. So this is like oh yeah, this one. So each tweet has a couple of like dozens of properties and fields that you can encounter. And sometimes it's worth combining all of them together onto a single line. What you're trading off here is you're making each tweet self-contained so that you don't have to reference anything else. So in the previous format, you have tweets in one section, users in another section, and multiple tweets can reference the same user, or multiple users can be involved in multiple tweets. And that makes sense from a kind of if you have separate tables and it's a database. But if you're looking at it record by record, it's much more useful to have everything available in the one record, because then what you can do is rather than processing things one response at a time, that's a huge chunk of data, you can process it one tweet at a time, which is much more compact and much smaller. So you can distribute things much more efficiently if that's what you're doing. But we're not going to go down that road today. We're going to go do something slightly different. So Twark CSV takes this JSON highly nested, deeply nested kind of format of data and turns it into a single table, like a flat CSV file. So all of the properties kind of more resemble this, where each tweet will have all of its properties in a single row, and all the columns will apply to all the tweets. So sometimes you'll encounter totally blank columns, other times everything will be filled in. But all of the records are then exactly of the same type, which means you can manipulate things a lot easier. The disadvantage of that is that it eats up a lot of memory. So once this finishes, you end up with like a usual CSV file with, I think it's like 80 or 90 columns and a whole bunch of data. I think can't remember how long this takes to run. It should be quick enough, but it's useful to know just to see. All this command does is count the number of lines in the file. So this is the CSV file that we pre-processed, and it's taking a while. Maybe. Oh yeah, it didn't run. There was another cell I didn't run earlier just to show you, to give you an idea of how these files change. You've got the same data, but in different formats, and you're trading off disk space for the ability to read it quickly, or the ability to interact with it more efficiently. So there's a couple of files in here. So the original data set, the one that I downloaded, this one is 3 gigs, and it's a bunch of requests, a bunch of results, just straight from the API without modifying anything. If you flatten it, as in, if you make it 1 record per line, if you get rid of some of this nested structure where you have turn it into this, where it's like 1 tweet per line and the tweet is self-contained, obviously you'll get a much more duplication. And you see it grows to 8 gigs suddenly, because all of a sudden there's so much more duplicate data, because multiple people can tweet multiple times, and the same values keep reappearing. So you can see that once you start looking at it, there's a lot more data here than you originally thought. Thankfully, though, for storage, JSON data compresses quite well. So you can get this 3 gig file down to just over half a gigabyte if you store it in a compressed way, which is kind of useful to know, because pandas will also read straight from, you can also read these straight in. You don't have to like do this step of converting it to this really inefficient format at all. This is just as an illustration of just how much data is in there. And the CSV is very similar to this one, except there's less kind of syntax. You see, JSON file format has a lot of brackets, a lot of quotes, a lot of spaces, commas, and all of that. CSV is slightly simpler, so it's slightly more efficient. That's why this file is a lot smaller than this one, but still, it's bigger than the original, because you flattened the data and you've repeated some values, or you filled in just blanks for others, because everything has to match up then. Every single tweet has the exact same properties as every single other one, which means that you can operate on things column by column, as opposed to row by row, which is much slower.
Igor.
Yep.
And for people who don't necessarily work with Twitter data, but end up with a JSON file, let's say. So when it's highly annotated, will you recommend that for readability, that they always flatten it, or that they always work with a CSV or a data frame rather than keeping it in JSON?
Yeah. So I would, Right. It depends on what you want to do with it. So I would keep it as the original JSON as much as possible, because then when you build your pipeline, everything will be reproducible. One of the most common kind of pitfalls of all of this is that you generate your CSV file from the original and you do a bunch of manipulations to it and you edit stuff and you add extra columns and you derive columns from other ones. And all of a sudden, when you get new data coming in, you're no longer able to repeat the exact same steps you did to get this file, and it makes it a lot more difficult. That's why it's always worth separating the steps that process the original data into the CSV, and any kind of manipulations you do on the CSV file, which is just a format that's easier to use because all the libraries expect it. And you could just as easily load this kind of JSON one per line file too. But CSV is just more widely supported. So I would make sure to keep the original data in its original form and make sure that when I'm running stuff that the CSV file that I end up with, I don't treat as the ground truth. It's just something that I look at. It's just a view of the data. It's not, I'm not going to be holding on to this CSV file. Like once I'm done doing something, I can throw it away. But I'm definitely keeping the original data in its original format, and all of the steps that I apply to it, I'm going to keep in like a pipeline, which is a bunch of command line commands in this case. But yeah, yeah, anyway, that's how many tweets we have in total. There's like 1,600,000 something, and they're all in the same columns, and there's a bunch of different metadata in there, and a lot of it isn't useful. So maybe if I show you something first, yeah, it shouldn't take too long. Okay. This is just to make sure that we can see everything in that Pandas is showing us. While this runs, so this is the naive way of doing it. This is just me showing you how much memory it can eat up if you load in. This isn't even that many tweets. Usually you'll be working with something another order of magnitude more, maybe tens of millions or hundreds of millions as opposed to a million.
And that's another doubt that I have. Sorry, but for interrupting, yeah. But I like to also know myself. So if I'm working now in Colab, let's say, but I'm also limited to how much data I can upload there, right? To my drive.
Yeah, that's right. Yeah, and that's another good point. So Drive, I'm using a Google Drive that's from the university, so I get way more resources than the normal. I think the default one is something like 8 gigabytes or something, which I've already chewed through with that one single file. And it's taken its sweet time loading stuff in. Actually, while it's spinning around here, I put this in just as a reminder. So Colab has a bunch of libraries already pre-installed. If you try to run a notebook locally in your own environment, you might find that you don't have Pandas and you have to install it. And the thing about Pandas versions is sometimes they're incompatible with one another, especially if it's like version 1.3 point something might be incompatible with version 1.1 dot something or 1.4 dot something. These kinds of major revisions usually break things. So if you've got code that works in 1.3 dot something, it's not guaranteed to work with like the latest version, which is I think 1.5. So that's another thing to look out for. If you are taking an existing notebook from somewhere or an existing piece of code, there's always going to be a set of versions that are going to work for it and other versions that are either too old or too new for, and things will break. I think I have an example of that at the end with a library that I wrestled with a lot, because it's got very specific kind of requirements that you need to downgrade things for, which is really annoying. But anyway, the full set of records that it loaded just now is just shy of 8 gigs. So if you're running this on like an average laptop, it wouldn't fit. It just barely fits on Colab. I think we just barely missed the RAM limit, so it didn't crash. Because this number is also slightly misleading in that it's actually more than this figure, because there's other temporary objects that get created when you read a data frame and all of that. But that's the full thing. This just deletes it as soon as it read it, just to get rid of it so we don't run out of memory while I'm showing you stuff. Anyway, yeah. One strategy that you can do is simply not read all of the data. That's, I think, the simplest thing to do. Is if you're finding that the data frame is too big, just don't read it all. Read a portion of it. And you can do that in various different ways. A very good, reliable way is to randomly pick which rows you're going to read. And the reason behind that is that if you pick sequentially, so if you pick the first 20 or the first 20,000 rows or whatever, you might get, like, first of all, they're arranged, the way the data is, they're arranged by date. So you're gonna only get tweets from a certain time range. I think it's reverse chronological originally. So you're only gonna get like the newest tweets first or the oldest tweets first, depending on how you processed it. So it's always worth considering that to get a more representative sample, you need to randomly pick the rows from the file. That way, the properties of the data will be retained. So the idea is that you, rather than taking the entire data frame all at once, you randomly select a bunch of rows from it, and that random selection is going to have similar properties to the full thing. So whatever kind of insights or whatever kind of quirks that come up in the original are likely to come up in the smaller sample too. They're not guaranteed, but they might. And this really helps if you want to do this so that you're much faster and much more interactive when working. Because when working in notebooks, ideally you want a cell to not take longer than a couple of seconds to execute, because then you're much faster in adapting things and changing things and adding to bits. So just to give you an idea, there's various different ways of subsampling a CSV. I actually like not this way. This way does it in Python, I prefer to do it in the command line, which I find is slightly faster. I'll show you why now. So I've started running this thing. It's reading the original file, and I've told it to get me 10,000 records out of the 1.5 million or whatever. So now it's running through the entire file and randomly picking out rows and reading them into a data frame and giving it back to me. It's still going. There we go. So we've got 10,000 random tweets, and it's a lot smaller now, just 60 megabytes, but that took a minute to run. Whereas something else,
Igor,
yeah.
can you please can you tell us about the memory usage in that command? So
oh yeah, the memory, yeah. So this df info, when you open a data frame in Python, every single row is stored as a separate every single column is stored as a separate thing. So it goes column by column. Every column is an array of values, and every one of those values has to live somewhere in RAM. So what it does is, Pandas is very good at keeping similar things together. So an array of lots of integers is going to be nice and efficient to pack together and store in memory. Text takes up a bit more, but if Pandas knows that it's text, it can optimize it slightly better and store it all together so that it's easier to read and uses up less memory. But usually it takes more resources to figure out how much memory is being used than just guesstimates. So normally what, let me see, I'll add a new thing just to show you. So normally if it roughly estimates stuff, it gets it wildly wrong. Right now it's saying that this data set is only using up 6 megabytes of RAM, which is wrong. The parameter that was there, the memory usage deep, that goes through and tries to figure out every single object that it created and account for it. So it's a lot more useful, but it's a lot slower to run, even though both are quite instant. So I don't know. That only comes in when you're doing other stuff. The verbose thing is about, this will give you a readout of every single column that it's storing and how it's storing it and what's in it. So we have a bunch of column names, like the text of the tweet, there's 10,000 of them. And right now it's storing everything as an object. It doesn't know anything about the data. So there's a bunch of other fields in it. It doesn't really matter too much if you know this format or not. I'll go in and explain it in a second. It's more about the process of you going through and looking at it that's useful, not the fact that you already know it. So anyway.
Okay. Can I add something as well? For picking a random sample in your data set, can you then also just randomly create an array with numbers from 1 till the end of your, like the number of rows of your data set, and then pick those, use that array for picking the tweets?
Yeah, that's exactly what it does. Over here, well, it actually does the inverse of it, but it's the same idea. It randomly generates all of the row numbers from whatever total there is and skips them. So it's so it doesn't have to read them. It's more efficient to skip rows than it is to read them. So and you have to apply it to the whole thing. So it that's how it works there. What I actually prefer is not to do it in Python, but to do it in the command line. This takes slightly less time because then the file is saved permanently and you don't have to read the entire file all at once. So I made a 10,000 and 100,000 subsample where I take the first line of the file, the header, which you always want to include, and then append 100,000 or 10,000 or whatever random lines from the same file into a new file. So just to give you like an idea, if you want like a random 1,000, it'll take a minute as well, but you're only paying for this execution time once, whereas with the other approach where you're relying on Python to generate a random sample, this is going to have to run every single time you reload the data frame, which might be a few times, because you should be expecting to constantly have to restart the runtime or do something else and be interrupted or run out of credits, or something else might happen where you need to start from scratch. So you want to persist as much of the computation as possible and save the intermediate steps too. So anyway, the 10,000 tweet subsample is the thing that we're gonna kind of start working with now. So we got like a rough idea of what's in it. We've got all these columns. We had a look at the memory usage, and it's pretty bad. So we want to see if we can squeeze this down, because remember, this is just a very small portion of the original, and we want to be able to fit the original into a single data frame and do something with it. So we're gonna take a small subsample, see what we can do with it, and then run the exact same thing on the full thing. So once we have our smaller 10,000 random sample, we can pick out another random 10 records from it just to have a look. This step, I think, is underappreciated, where you just kind of, let me give it fewer records so you can see. This step, I think, is underappreciated, where you just look at the data and see what's there. So we have our rows, we have our columns, and there's a bunch of stuff in here. So there's some IDs, there's some more IDs, some of them are missing, and you can start getting a sense for what's in here. So straight away, you see that there's large integers as IDs, lots of missing values, some more integers for other IDs, some dates, the text of tweets, and some other metadata that might be useful to know, like language, the source, I think, is where the tweet was posted from, maybe some count metrics, and there's a bunch of other stuff in here. Some of it is still not fully flattened, as you can see. So this is a list of things, and it's still in the original JSON format, which we might want to process somehow later on. There's a whole bunch of other metadata that may or may not be useful later on. We don't know yet, but it's all in there, and there's a lot of it. So how do we figure out where to start trimming this up? where I usually start is with this describe all command. That gives me an idea of, well, just the counts and the unique values of what's in there. So if I see that the count and the unique columns match, it means that every single row is there's no repetition whatsoever. So that's usually something that's unique to every row. So that's definitely a good thing to keep as the ID. If there's fewer unique numbers than the total, it'll depend on what it is, but it can give you a clue of whether to encode this as a category or maybe something else. So you have to kind of look at how many unique values and what is the frequency of the most, like what's the most frequent value. So over here, the most frequent value occurs once, so they're all unique. Over here, this value occurs twice, so the conversation ID is obviously not unique, so 2 different records or 3 can have the same conversation ID, and so on and so forth. It goes on across all of these like that. So some of these you can see there are zeros and those are columns that are good candidates for just getting rid of entirely. There's no useful data in there. They're just empty. These are just columns that are there because of the data format, and you can safely delete them. They're not adding anything. Other columns have, well, these are almost unique. So the created timestamps are, as you'd expect, are all unique. So very little chance that the same tweet is posted twice, you know. Other things you might look out for are something like lang or source, where you have all the records, but only very few unique values. So these are good candidates for turning into a category type in pandas, which is much more efficient than the default. We'll see it in a second.
One more thing I think it's interesting as well is when working with this kind of data that it's so that the timestamp is also so detailed, then maybe you don't need to be keeping all that information, but maybe you want to work, okay, I only want to include tweets about this day, and you don't mind about the hours, or maybe about these hours, but you don't mind about also like the milliseconds. So also you have to see how to process that so that it's easier for you to read as well the data and see how to classify it in buckets if you need, or for a timeline if you are working with that kind of data.
Yeah, that's exactly it. So that's exactly what the kind of mindset that you should be in. So you're looking at the data with a mind to do something. So right now, what we want to do is trim as much of it as possible while retaining all of the useful things. So let's just have a look at what's in here. The memory usage for every single column in this data frame. I think it's in bytes or something. Yeah. Here is a good kind of way to just eyeball what's taking up so much memory. So you're looking through the list, and the thing that jumps out straight away is the text, which makes perfect sense. Text, even though tweets are short, text is stored as an array of characters. So each character has to be accounted for and stored as a UTF-8 character, which is 2 bytes, is it? Or yeah, 2 bytes, right? So it eats up a lot of memory to store text uncompressed. Other fields where everything is 0 still take up memory, because you still need to use memory to indicate that something is missing. So if you get rid of it entirely, you can save yourself a lot of memory by just not having this stuff. These are columns that were introduced into the tweet format recently. Recently, Twitter brought in a feature where you can edit a tweet, which isn't really editing. It's more like creating a new tweet and hiding the old one, because everything else is built on the assumption that they're immutable, and it still works that way. But it's a kind of hack that they've implemented that works quite well and makes a lot of sense. But anyway, the point is that old data sets won't have these fields. Like, this is an old data set, so it won't have these new fields filled in at all. So they're always going to be empty. So it's safe to trim these away when we're loading the full data set, and that will give us a big saving in memory. Just kind of eyeballing other stuff, there's a couple of other things that are quite large. So the entities in the mentions entities are quite big as well. Well, they derive from the text, and in the original data, if there's a mention, I don't think there's one here. Maybe there's one here. Let me see. Just to it doesn't have one when you want it. All right, so maybe this one does have a mention. So the reason it's big is because it's storing an ID and a username and indexes where it appears in the tweet, and it's got a bunch of kind of syntax around it too. So it's actually storing 4 different things as opposed to just that. But we already have this in the text file or in the text field. So this is just metadata for convenience. We can always parse this text and extract this from it, and look up this value from the users down below to get the ID. So technically, we can also get rid of this. If we're not using it directly, we can get rid of it, and it's quite a big chunk too. Other stuff in here that jumps out. URLs are quite long as well because they're text, and this one is huge, the Twark URL, and this is just metadata that Twark inserts itself, or that we put it in there on purpose, so that it makes data provenance much easier. It means you can have an idea of exactly what request was sent when and how you got that data. And for this case, it's not that useful. So we can save a lot of memory just by getting rid of it. And that's what we're going to do next. So
Igor?
Yeah.
I have a question. I was thinking about the mentioning again. If you mention someone and you do an add any text, of course, that can also refer to locations. But like you mentioned, there's a list of users with a ID. But if the person that is mentioned did not post anything him or herself, would that person then still appear in a dataset with an ID?
Yes, yeah, it would appear because every single one of these mentions gets parsed in here with an ID, and then every single one of these IDs is matched up in the includes, in the users, and it's somewhere in there.
Okay,
and
great.
then all of the metadata is in there. And what we did earlier was, when we flattened it into a CSV file, is we included all of this information in the record in each tweet. So you see there's no mention here, but there's the author, and you got the ID and the username. That's going to be the mention or whatever. So all of that is like already stuffed in there somewhere. And we have the column in here. So we have our mentions, which has like the usernames and whatever, but we also have the the author ID, the author username, the author name. And if it's in reply to someone, we have the in reply to user ID, the retweeted user ID. These are all added in based on this exact metadata that is already in the JSON, if that makes sense. So we're not losing any data if that's what you're kind of thinking about. Yeah, so yeah, so right now we have 80 or whatever different columns, and they're all the same object type. Nothing else is in here, and there's nothing that Pandas has guessed correctly because I set it to not try and guess what the data types are. I just set it to always just assume it's an object. Just don't bother figuring out what it is, just leave it as is. I'm just gonna kind of run this again so that it's in front of me when I'm looking at it. So straight off the kind of what I was saying earlier, we can start getting rid of things. So we got rid of, start making a list of columns that you don't need. So the edit history ones that are always guaranteed to be 0. There's a bunch of other ones in here. What's this one? All the edit ones. There's an unnamed column because each record finishes with a comma, and for some reason it parsed it as an extra column, which is a bit of an error, but not too egregious. And this is just the first pass on looking at what can we get rid of. And I just eyeballed it and decided, all right, I'll stick these in and see what happens. Just from looking at it, what I'm doing here is I'm taking all of the existing data types and I'm just merging this with it. So instead of rewriting this entire thing again, so this big long list of matching the column name to the data type, I don't want to rewrite all of this. I just want to selectively do it. So this is a neat trick for merging 2 dictionaries together, the double star notation. So you, the open bracket thing creates a new dictionary and then fills the values, keys and values. That's the double star notation of the old dictionary and the new one. And the new one overwrites the old one. So in the old one, ID was the D-type object. And in the new one, it's going to be, I set it to an unsigned integer, 64-bit integer, which is a lot smaller than an object in Pandas. This is something that you kind of have to spend a bit more time with the data to know which one of these is appropriate where. So the unique values and the counts and the frequency and the minimum and the maximum of a value of a column will tell you whether or not something fits into like a 64-bit integer or a 32-bit integer, for example. So I know that tweet IDs are 64-bit integers, so I know to pick that one.
Igor.
Yep.
And if you don't specify a new type for one of the columns, then it will keep the old one.
Yes, that's it. That's the, yeah, I want to do it step by step because I don't want to lose any potentially useful data. And I want to kind of iteratively go through it and see what happens. So that's why I'm doing it this way. Kind of pretending that, yeah. The difference between, there's a subtle difference here. There's a small u int 64 and a large u int with a capital letter 64. And the difference is that this one can't be null. So it's only reserved for columns like this, where every single column is filled in. So the ID can be this smaller variant, which takes up less memory. But this one that's not unique to every single row can't. So this one has to be the capital U int 64, which has an extra, it's 64-bit integers, but also nulls. So it has a marker in it that will accept blank or missing values. And you'll see why that's important in a second. They actually do have a different kind of memory usage, the two of these. So sometimes it is worth investigating whether or not you can get away with something more efficient. But anyway, that's all I put in. I got rid of maybe 4 or 5 columns and just changed the type of a couple of these. And I spotted that 2 of the columns were dates. So I'm gonna tell pandas to try and parse those as dates too. And well, text is always going to be a string anyway. The useful columns are going to be all of the columns from all of the original columns if they're not in the list of removals. So that's kind of a slightly awkward and long way of doing it, but it means I'm not repeating myself. I'm not specifying the same columns multiple times. I could just write them once in either the remove columns or in here, and it'll know what to do. So now with this 10,000 sample that was like 60 megabytes, we're gonna load it, but tell pandas to only load the subset that we've defined above. So we do the same thing as before, and suddenly it's down to 53. So we've shaved off a small kind of chunk of it. And now we have a slightly smaller data frame. Still kind of unwieldy and still not optimal, but still worth kind of investigating. So next I want to see if how many of these fields, like how common are missing values. And you can find columns with any missing values in them with this command, just is not applicable any. So if there's any missing values, it'll say that it's true beside the column. So I know that all of the IDs always exist. The conversation ID always exists. The author ID always exists. So these are good candidates for always keeping because they're unique and there's no missing values. But all the other ones, there may be some stuff missing. I mentioned earlier that some of the columns that I removed, like the edit history one, where everything was guaranteed to be missing, and maybe there's other columns like that. I haven't looked through them all, so this command gives you a good shortcut to figure it out. So this will find columns where everything is missing. So it's false for the ones that have some values, and lo and behold, there's another row or there's another column where everything is missing, and it's the context annotations, which I explicitly set to not retrieve because they're huge and they eat up a lot of resources. So we can safely get rid of this entire column and save ourselves some memory again. And there's a bunch of other ones. This is some metadata about when Twitter has to ban certain accounts in certain countries or hide tweets for copyright reasons. And those are very rare. So the columns are there because the data format has them, but we can get rid of them for our analysis. So it's safe to dump these too. Matching rules is another one. That one comes up sometimes in when you're streaming, but since we use the search API, it's always going to be blank. So now, armed with that information, we've added more. We can start looking at like this describe all now has for the number columns, it now gives you some extra information, which is somewhat useful, I guess, for some of the other numerical columns. Let me see. All right, no, it's these ones that are here. Yeah, so yeah, sometimes it's useful to change this format to not be scientific notation because it's kind of hard to read in this one. But anyway, we'll keep going with the rest of the stuff anyway. I've added more of those blank columns to remove, and I've also added a couple of other ones that I thought weren't too useful. So there's a couple of columns in here where there's only like 2 values in there. Like the geotype is always going to be place. I'm not really interested in the bounding box for a place because those are fixed. Those are just drawn like arbitrarily for every place ID. So it's the same as just having a place ID. You don't, unless you're doing some kind of thing explicitly with geo information, you can dump this stuff, and it's just a bunch of numbers that define a polygon for an area, and I'm not really interested in that. I already have the location as a name, which is more useful to me in this case. So that's why I'm dropping it. And I've added more types now. So I've noticed that there's more IDs that are 64-bit integers, but there's other numbers in here that are quite small. So there's public metrics for these are counts of like friends and followers and how many times somebody tweeted and how many lists they're on. And it turns out that you don't need a 64-bit integer to represent them. You can get away with 32-bit, which cuts the memory usage in half for it. And the listed count doesn't go above, I think it's like 65536 is the limit for the unsigned one, which would put it over. But so you can get away with storing it with even less memory. And other things like whether or not an account is verified can be stored as a Boolean as opposed to a text field, which it was originally, which saves a lot. And each one of these, a category in pandas is special because it's much more efficient than just leaving it as an object, because it stores each category value once and just has pointers to it in every row, if that makes sense. So it saves a lot on memory. And there was another date for when the record was retrieved that I put in. So now that we have our even more expanded set of columns that we're interested in, we can see where we're at now. Now we're down to 12 megabytes, down from, what was it, 60 originally, which is starting to look much better. So now we can have a look at the columns, and this is how much memory each one of them is using up. So all of these IDs, as you can see, use up more or less the same amount of memory. The text uses up the most, obviously, because it's where most of the data is. All of these counts are now way down. For some reason, the quote count, oh, I missed the quote count. So this one is still being stored as an object. Actually, this gives you the perfect kind of representation of how much memory you can save by explicitly defining the data types. So this is explicitly defined as a like a 32-bit integer, and this is an object. So you can see the size difference or the memory requirement difference between the two of them. How dramatic that is. And there's a bunch of other things in here that I could probably clean up. I got author locations, and there's another field that could do with optimizing. But I thought I added them. Added these, reloaded. Oh, no, I didn't add it. Well, never mind anyway. Well, let's add it now. So this one can go into in here somewhere. Where we get. And we'll make it the same thing as that. Oh wait, it was already in there. Was it public metrics and quoted can't, was it? Yeah. Oh, maybe it is just a large, it was already in there. Never mind. It wasn't due to the memory usage there. The type. It was something else. Well, anyway, that'll probably do for now. Going from 60 to 12 megabytes is probably good enough for now. And now we get to see, we're loading the same full data set now. And this might take another minute or two because it still takes the same amount of time to iterate over the CSV, but now you are loading less, keeping less data. You're still reading the same amount, so it still takes the same amount of time to load it, but you're not keeping as much. And once it's, it should only take a minute. Oh yeah, there's a couple of other interesting parameters here. So the low memory false parameter when reading a CSV means that it'll try to read the entire column all at once. And this is useful if you have enough RAM to go around while loading, because it guesses the data types more correctly for the columns that you haven't defined in the D type thing. So our D types are the ones that we manually defined, and this sets the setting that gives it a bit more memory to work with when it's guessing. And the rest of them are for parsing what and where. So there we go. We're almost there. When I was running this earlier, I was trying to get it so that it would crash and then wouldn't crash, but I think it's better if it doesn't crash this time around because I don't want to rerun any of the stuff. So you can see the memory is getting used up, but it's also dropping. So it's reading stuff in and then discarding the stuff that it doesn't need. And it's going row by row and extracting stuff and getting rid of stuff. And it should end up with a lot smaller, with a much tinier data set in the end. So while it's running, oh, actually, it's finished. That's fine. I was going to scroll up to kill some time, but if you remember, the original was something like 7 or 8 gigs, and now it's down to 2, which is perfectly fine to kind of store in in a kind of laptop or on your own workstation, and that's a lot more manageable. Also, another kind of interesting thing is that you can read directly from compressed files. So because the CSV is very kind of bulky, you don't want to store like 8 gigs of text on your hard drive. If you compress it, it's only half a gig. So that half a gig gets stored somewhere there, and you can keep it as an archive that way. So just to kind of eyeball the data again, same thing, same tweets, except now it's a subset of columns, and it's a much smaller. We have a look through. Yeah, it's working out all the different number ranges and stuff for all the numeric values, which, well, they don't really make sense for the IDs, so it's kind of useless here. But for some of the other stuff, it's slightly more useful, I guess. As you can see, there's still some columns that are left over unflattened because they're lists, because otherwise it would be unpredictable of how many columns you're going to end up with, because you don't know how many of these you need. But these are things that we can kind of ignore for now or leave till later. Now that the data frame is slightly more manageable, we can use something like Vader to give you a demo of what it's like to add stuff on as opposed to remove it. So Vader is a really dead simple sentiment analysis approach that just has 2 dictionaries of positive and negative words, and it just counts them up and sums them together, and that's it. That's your sentiment scores, basically. It's really simple.
Igor.
Yeah.
I guess just to make it also more general, I would say, if I could summarize what you were saying, is also that depending on the context also, or the problem you are dealing with, you might have selected other columns to get rid of or to keep, right? And this, while this example is showing Twitter data, just keep in mind that what we see there is JSON. So that is what we will find in many other contexts, even if it's not Twitter data that we are working with. So all the processing, of course, the fields for the tweets are particular in this case of the example, and you might find other fields in your data, but you will have to go through this process, the whole thing of knowing what your data is, understanding what the values are in your data and which aren't, and what will you end up needing. I think that it's really what all this is about as well. So please, if you are not using tweets, don't feel that this doesn't apply to you, but it's the format of the data. What do you need from it? And you don't, that is really valuable.
Yeah, that's maybe I should highlight that a bit stronger, because I kind of, some of this does veer a bit too tweet specific, but that is the key kind of point, that it's the process of this kind of loading a subsample, looking at an example row, figuring out, do I need this or not? I can drop it, go again, and kind of this kind of repetitive thing of selecting things over and over. Anyway, the Vader thing is not really that important. It's more just to demonstrate that you can do other stuff on top of it and enrich the data somehow. And there's a couple of gotchas that come up with it. So yeah, as I said, the way Vader works is just, it takes the text and counts up the positive and negative words it encounters and just sums them up in a kind of smooth way, in a in one of the variants anyway. So what we want to do is we want to add a sentiment column that is based on the text and apply it to the analyzer's polarity scores function. So this will go through and this will apply the same function to every single row all at once. So it'll take like a while spinning around, and sometimes you don't know how long it's going to take, which is not ideal. Ideally, you want, once you start doing operations like this, it's worth kind of reconsidering doing it blind. So I'm gonna stop this for a second, and I'm gonna install a really good tool called TQDM, which adds progress bars to these kinds of operations. So you get an idea of how long something's going to take, so you can stop it in case you're going to be waiting here for like days or something. And the way to activate it is just to import the pandas kind of add in and change the command from apply to progress apply, and that's the only difference between this one and this one. And in here, actually, I noticed that this was taking a while to run, so I'm gonna make let me see, I think I have to reload. So because I stopped the execution earlier, like I mentioned, I have to go back and rerun some cells.
Igor,
yeah,
there is one question. So yesterday I showed one example of sentiment analysis, but done with Spatie. So they are asking, so there is a question from Marike. She's asking what features, what is different when using using Vader than when using Spatie?
Vader is much simpler. Vader is really it's simpler and it's more tuned to tweets. So the Spatie sentiment analyzer by default is more generic. It's got it's trained on news articles and reviews, I think, whereas Vader is tuned specifically for tweets, and it's got a bunch of a lexicon that was like manually annotated based on tweets, so it's a lot easier to work with that way. Actually, something is being really slow here, so I am going to restart this. Let me see. So yeah, this is a perfect example of why, after running some memory intensive or some CPU intensive thing, sometimes the background Python process dies and you just end up staring at a spinning kind of thing. You kind of get a sixth sense for when things break or how long a cell should take to execute. So we don't need to load the full thing again because we know how big it is. We do need this. We don't need to show you again the 60 megabyte version. Then we did the 60 megabyte version loaded slightly differently. Then we did some more cleaning. We got these types. Oh wait, we didn't need to load it after all. Let's load this one just for just so it has some kind of data frame in the memory. There we go. So now it should work. So these are all our types. We did some more sampling, or more looking at the data, more describing it, more removals. We read it again. This was more looking at stuff. And this was the final kind of smaller data set that is now loaded in properly. And we don't need to do this again because we already grabbed the smaller version for Vader. So given this 12 megabyte kind of small sample, the 10,000 entry one, running Vader on it was still a little bit slow. So I decided to kill it and stop it and see what the deal was with it. And once Vader is loaded, running this didn't really work out. Either, I don't know, it just slowed things down too much. So we installed TQDM, restarted our runtime, and reran everything. So now we can import the TQDM thing for pandas that runs in Colab, subsample it again and give it a tiny proportion of records just to test the code, just to see how long it takes and whether or not it's feasible to even run this thing. So we have a tiny sample of 1,000 records in this df tiny thing, and we're going to add a new sentiment column that's based on the text that applies the polarity scores from the sentiment analyzer using a progress bar. So now we have a better idea of how fast it is. So it gives us 3,000 or something items per second, which is useful to know later on. So it's very quick at generating sentiment scores for 1,000 tweets, but obviously for 100,000 or 10,000, it's a good bit longer. But how much longer, we'll figure out now. Just so we can see what's going on, I'm going to set it so that it doesn't hide anything when you display just the text and just the sentiment. So this data frame is still containing all of the records there, but it's just showing you the text and the sentiment. And if it decides to, I think it's this step that's taking slightly longer. So we need to reset the index because this is a sample of the original and all of the index numbers are now all over the place. So we need to kind of get it back so that it's 1, 2, 3, 4, 5, 6, 7 or whatever. Something else went wrong for this thing. I'm not really sure why. Let's just run it again and see what happens. Maybe yeah, this is the other thing that sometimes happens. Sometimes after a couple of back and forth things that are running, Colab tends to kind of grind to a halt, which is never good, but that's just something you have to live with. So I think I will see if I can stop this and maybe show you. Let me see. Yeah, I think it's yeah, it doesn't want to. Let's see if we can coax it back to life. I think at this point, my browser is starting to not like the fact that I have so many cells displaying and so much text on screen and all of that, and it's running out of memory. So anyway, oh yeah, I think we need to run this again and then this. Well, anyway, this is almost at the end, but for some reason it's not cooperating. Anyway, while that figures itself out, the rest of it is relatively straightforward too. So what we're doing after this, even though you can't see it because for some reason they just decided not to want to run, what we're doing is if you could see it, it would be a separate sentiment column that we can split into the components, the positive, the neutral, the negative, and the compound score. And let me see, maybe it wants something else. Yeah. So maybe if we reload the data frame. So we have this one, we have this one. Yeah, this is the part where the limits of Colab become apparent, or even after like a couple of dozen cells, it starts kind of breaking. I'm just going to delete some of these describe and other sample ones. I think it's having trouble displaying everything all at once. Gonna go back. Yeah, that's the other thing you sometimes have to manage. So because it's in a browser, you are limited by the resources that the browser has. So sometimes the browser has limits on how many cells it can render, how many windows are open, how many things at once can be drawn on screen, those kinds of things. So the kind of thing to consider there is if you are exclusively going to be working in a browser in Colab, let me see, let it save first. You should be aware of these limitations. The alternative is that instead of working in Colab, you write everything as a Python script. So you write Python files that you then execute in a command line and kind of have a more traditional software development life cycle and framework and everything else, where you don't have this kind of notebook idea where you write tests, you write your functions, and you execute the thing from start to finish, and you don't have this kind of interactive thing going on. So the advantage of that is that you avoid things like this, but the disadvantage is that you don't get to mess around and play around interactively with data that might be easier. Well, it's easier if it's not displaying. Well, it is now. Okay. So where were we? Our tiny data set with sentiment, our tiny data set with sentiment applied to every single tweet. So you see, we've created a new kind of dictionary with all of these values and appended something new to the data frame now. And now we kind of turn this mess of JSON into something slightly more readable, where you have the text and the raw scores for the sentiment for every tweet. And oh yeah, and the next part after that, I had just to show you how these things work. So now that we know that this thing runs roughly at 3,000 or whatever something items per second, we can apply it to the entire data set, but that takes too long, and we've already kind of waited for this thing for too long. But anyway, we can do the same thing to a larger data set. This is now 100,000 as opposed to the 10,000 or the 1,000 one, and it's the exact same thing, exact same steps, and off it goes, and gives you the exact same result. And you'll have the same thing as this, except now it has been applied to the larger chunk of it. And the step after this obviously is to apply it to the whole thing, but I'm not going to do that because it takes like 20 minutes to crunch through the million tweets or whatever. Anyway, that is I think that's all I wanted to go through. So it's more about like, obviously if you're doing this for tweets, it's very applicable because you can just copy directly what I've done. If it's not about tweets, I would focus on the steps where you read a bunch of data, you look at the memory usage, look at the values of it, the types of it, add, get rid of stuff, mess around with it, and see if you can squeeze a bit more performance out of it just by getting to know your data set a bit better. There's actually quite good tools to do this semi-automatically. There's where is it? It's called Pandas Profiling. It's a library that lets you I'll stick it in here. In a couple of lines, it basically emulates what we've just done in a couple of those cells, and it'll give you a nice kind of user-friendly interface to look through all of the values that you have and have a nice report. Maybe there's a demo of it here. No, it's not. I thought they had a demo report somewhere. But anyway, it's just as an aside, that for every single one of these things that you end up doing, there's probably a good library that helps. So I didn't want to use this one straight away because I think it's worth digging in and doing things manually and having a look at exactly how you mess with these things to get an appreciation for exactly how even changing the type of a single column can have drastic results and suddenly make an analysis viable, as opposed to if I were to use this Vader thing on the original data without cleaning up any of it and without optimizing it, it literally takes like a day or two to run. I tried it before, and just to see and it kept crashing because it kept running out of RAM, and was just too slow because every single record has to be passed back and forth, even though it's only working on the text field, because the data frame is so huge, it's taking up the rest of the RAM, and there's not enough for it for other processes. And other stuff like splitting up the data frame and processing it in parallel didn't really help either, because of the whole thing with the single core in your single core CPU. So you're not getting any advantage from that. And that kind of trimming and optimizing the data frame type, I think, is the most bang for your buck for cleaning up this stuff and making sure that the data set that you get is actually runnable in Colab. I think that's all I wanted to go through anyway.
Yeah, that's great.
there's
Thanks, Igor.
Yeah. Oh yeah, I didn't upload this exact notebook to the GitHub repository, but I'll do that in a minute now. I think my browser is starting to give up.
Yeah.
It's just in time.
Yeah, your data needed some more cleaning.
No, this is the worst limit, I think, is I'm
just messing with you. No, I really appreciate it.
It is true. Like I have I've encountered the exact same thing before. After working in a Colab notebook for longer than an hour or two, it just starts breaking, and you need to restart your browser to start closing stuff and clearing caches and stuff like that, and it's really annoying. So I guess the kind of alternative to it is you can do the same thing running Jupyter Lab locally, I guess, because all Google Colab is just basically a Jupyter Lab instance with a fancier user interface. You can get the exact same thing running things locally on your own computer, like this one. So you have your notebook. I still have a Wordle thing open from a while ago. Never mind. This is something else entirely, but it's still the same deal. You've got your notebook cells, you've got your kernel, everything is running here, etc.
I think one thing that I'm left with in you and we can see it nicely in your session is that we spent an hour and a half probably, going over the data until we had it to a point where we could do something with it, I think exactly. And I think that represents a lot of how the process goes actually, and how it should go, because if we take the data as is, we also feel, I've encountered it myself, when we just take a data set without really knowing what's in there and what we will end up using, it can overwhelm us as well. It's so much data, and you end up thinking there is nothing for you there, but it is. So it just get rid of what's not and keep what you need. In this case, imagine if we were only to do sentiment analysis on the tweets, maybe what if I only keep the text and like say I don't need anything about when it was posted, all of that, if it happens to be that I needed maybe over time, or that I need to know who said what, then it changes things, because I will need the date, I will need who posted it. But if I need to run, to understand out of this data, what I need is to understand how people felt about it, then maybe I just want the text. So to give you an idea, and I think it's a very nice, true way of seeing it, how much you have to spend on understanding your data to get to do something with it.
Just to give you an even more kind of realistic idea, I think in total, I didn't really time it properly, but going from start to finish, even with me having a really good idea of the type of data and how it works, to go through this whole thing was more like 5 or 6 hours, not the 2, because the 2 hours I spent, I had already written everything, right? And I was just stepping through it. But in order to go from like very, very beginning of zero, like the blank notebook, and start kind of poking around, if you include all that time and all the failures in between, where I spent a while because pandas profiling, which I wanted to use, kind of broke for me because it was too new and something else was too old. And let me see. I wonder if it'll work now, because I think I finished it earlier. And yeah. So this is just like an example of another tool that is helpful for this process, that aims to automate some of it and give you a nicer user interface for it. I'll leave it in there anyway. It's a little bit cumbersome though. See, it kind of touch and go sometimes. Yeah, it ran out of RAM, so clearly not there yet.
So yeah, so maybe let's so to take advantage, because we already went a bit. It's great actually. We could keep talking about this, but we have some. We are a bit over the time, but we have some questions. So Marike, is there a difference in storage of tweets that contain emoticons? And for sentiments, are emoticons included in the assessment with Vader, for example?
Yes. So the emoticons and everything is stored in, it's all in UTF-8. So like this globe thing is actually a UTF-8 character. It's not like the image itself, you know, it's the image is rendered by the browser, but the raw text here, like maybe if I get this one, and where was that? I had a nice tool for UTF characters for showing them. Let me see.
And maybe on top of that, is Vader also, can I also apply Vader to other text, even like short text, or is mostly for tweets?
Vader sentiment. So Vader does have, it was trained on tweets, so it works best on tweets, but it actually works quite well on other social media text. So Reddit posts, comments, YouTube comments work quite well with it because they're also short and have kind of hashtags and things like that in them. You can have a look of what's in there. It's a really kind of straightforward and simple lexicon. So we have a bunch of emojis, a bunch of words. Well, it's all of the emojis for those, and each emoji has like a score, and all of these kind of smileys have scores, and all of these words have scores, and that's really just how simple it works. So as long as your text has this kind of vocabulary, it'll work. So you can, it's very straightforward and actually very hard to beat for social media data. Vader is still like the simplest and the easiest to run, and very difficult to, like, you really need to try to beat the quality of this thing. I think the one that did beat it was some really complicated neural network that you need a GPU to run, and it's just not worth it if all you want is just a rough idea of whether or not a sentence is positive or negative. Like this one, let's go. Such and such are a scam. I booked a holiday, now it's gone. I haven't heard anything, and it's negative. Whereas this one is like, where's the big positive one? This one. Well, it's not that positive, but forward looking maybe. But yeah, sentiment itself isn't that kind of exact anyway, but
Yeah.
Vader's quite good.
Yeah, any other questions or comments on what we saw? Yeah, also, yeah, Igor is always there. We can get in touch with him. Remember
Yeah.
him when working with Twitter data. He's the guy.
Yeah, if you've got any like specific questions about Twitter data or whatever, feel free to either like DM me on Twitter, or best thing to do is probably to go to the Twitter developer forums. It's twittercommunity.com, and like I answer questions there all the time. So if you have like Twitter specific things, just go there and I'll answer it. I'll see it. But for like general pandas questions, you're better off asking on Stack Overflow. That's like 90% of where you want to get answers is probably going to be on Stack Overflow.
Yeah.
Because the only kind of warning I would say about copying and pasting stuff from here is some of it is quite old, especially with pandas. So if you're on Stack Overflow and you're looking at pandas questions, the ones you find via Google are sometimes really out of date. So you'll get an answer that tells you to do it in one way and it no longer works. So for example, this one is the method chaining way, which is the brand new way of doing things. So if you've got an older version of pandas, this won't work. And because it's a new question, but some of the old questions where it's using the different kind of way of doing it may not work with the newer versions. That's the only kind of warning I would issue for this thing didn't want to run. But anyway.
Okay, I think that was
Yeah.
really great, Igor. Thank you very much for your time, for answering our questions. And
Yeah,
thank
no
you
bother.
everybody for being here. We have one more session left tomorrow with Ernesto, Igor. So yeah.
Oh yeah, I'll jump into that one.
So it'll be personalization and also how we can keep data that is sensitive, how we can keep it private and still personalize products or recommendations for people without having to invade their personal information. So also dealing with text. So I think it'll be a nice way to tie everything up. So thank you for being here, and thanks again, Igor. It was great.
No bother.
Okay, bye everybody.
Thanks a lot.
Bye. Thank you.
All right.